All right. Hello, everybody, and welcome to this week's GBO Colloquium Series talk. Today, I have the pleasure of introducing Dr. Eric Koch. He is an SMA postdoctoral fellow working at the Center for Astrophysics. And he'll be sharing with us his work on the galaxy M33 and how his studies of the ISM can inform our understanding of galaxy formation and evolution. So everyone, please mute yourselves for the talk. If you do have questions, you are welcome to unmute yourselves or save your questions for the end. And with that, Eric, please take it away.
Great. Thanks, Jesse. And this is showing up fine still.
Yeah, that's perfect.
Awesome. Okay. So thanks for the invitation to come speak today. So I'm going to, sorry, I'm just moving the camera around so I can see my own slides. So I'm going to talk about two different projects that almost span the full range of frequencies that the GBT observes at. So this is going to roughly be in two parts. The first part's a little bit more of a finished project, and the second part is very preliminary results from a project that will hopefully be finished once Argus is back on the telescope in the coming weeks. And so at the lower frequencies, I'll be talking about, you can see the map of the 21 centimeter of M33 in the top right corner. And I'll actually be talking about the part that is much harder to see or is less obvious to the eye, and that's the critical short spacing information that we get from GBT observations. And then the zoom in box is showing the second part. And I'll be talking about how Argus observations coupled with upcoming JWST observations will allow us to sort of understand what the anatomy of a spiral arm is from an external perspective at high resolution. So I picked the title of this talk to be just very general to encompass sort of the galactic in connection with the larger environment scales down to the scales of sort of parsec and below. And so the context and why I'm so interested in the local group galaxies is primarily due to their proximity. Well, they have interesting features on their own that are distinct from the Milky Way in several ways. One of their greatest advantages is it sort of it explicitly ties together the typical scales that you expect in galactic plane or all sky surveys of the Milky Way to the coarser scales that we measure over a broader range of environments in the nearby galaxy population. And over a range of multi-wavelength observations, we now have the ability to trace the ISM, in some cases down to almost parsec scales, while getting this external top-down perspective on the scale of the galaxy as a whole and sort of its surrounding environment. There we go. Okay. And so we can place all of this very broadly in the context of the larger galactic ecosystem for why we want to piece these portions together from large to small scales. And so I have a very simplified cartoon here showing the Baryonyx Cycle, the broad phases that is largely going on in a star-forming galaxy near the galactic midplane. And of course, one of the most important parts is that this isn't just a closed system. And critically, to sort of link to the secular evolution of galaxies through this process, we need to consider as an open system where gas can be added through different accretion mechanisms or lost through winds and outflows. And so low mass stars here sort of represent a sink. The mass isn't going anywhere. It's just not precipitating in the rapid cycling as frequently. And so hidden within this, and one of the greatest challenges is that there's a very broad range of spatial scales, sort of from the size of the galaxy and its larger environment down to the subparsec scales where individual stellar systems will form. And so I kind of want to focus on primarily the ISM components and linking the neutral ISM phases, the atomic and the molecular, and why that's important to bridge these large to small scales. So there are various observational and theoretical works on this importance, but I kind of want to just focus in on a few that I think make the point quite well. And so the first is that in the redshift 0 universe, the atomic gas becomes increasingly the dominant portion of the neutral ISM mass. So this is a well-known result showing that as we approach lower redshifts, the cosmic density of molecular hydrogen drops significantly, but the atomic component has maybe a drop, but it's not as significant of a drop. So if we want to understand the neutral ISM on sort of the galaxy scale as a whole, we really need to care about the atomic gas as the bulk of the mass. The link to star formation, however, really requires the molecular gas component. And this is obvious from a number of surveys. I picked just one here looking at the resolved Kinetic-Schmidt relations. In this case, this is kiloparsec scales. So these are from a nearby galaxy surveys from about a decade ago. And each point that you see in these plots is a kiloparsec average of the atomic gas surface density on the left and the molecular on the right, as traced by the CO2 to 1 line. So you can clearly see that the star formation rate surface density on the y-axis is really only correlated with the molecular component. And this is broadly what we expect if, in order to efficiently form molecular hydrogen, you have to have a minimum column density to attenuate the background far ultraviolet. And so we get this saturation point in the atomic gas. Now, the link to, I guess, larger galaxy evolution and why we need to care about this as an open system where gas and mass can be added or removed is that the depletion time that we find for current star formation rates in gas masses within the nearby universe is of the order of a few gigayears, depending a little bit on whether you're looking at the molecular or the atomic gas. And on galaxy scales, roughly going over the star forming main sequence, we do see that there is a trend on these on larger scales, but when we start to resolve galaxies, it's roughly constant. But what this implies is that to continue or to reproduce the star formation that we see in the nearby universe, we really need to consider what is being added to the galaxy. In this case, I'm just showing this really nice watercolor image from this review, showing what is expected to be the broad mechanisms surrounding the galaxy disk. So hidden within here is the actual galaxy or the star forming component. So we expect there to be accretion from the larger environment, outflows, and some recycling as well. So once we get down to the scale of the galaxy itself, the galactic disk, one of the main challenges remains in really linking this sort of galaxy to local scale features. And we still have some sort of conflicting results, including in some very recent work. So on the right, I'm showing the depletion times measured as in the FANG sample. So this is 100 parsec scales across a sample of nearby star-forming galaxies. And what we start to see is if we're resolving portions in these galaxies, we start to see that there are mild variations between different environments in these galaxies. So for example, the center versus bar or spiral arm regions. And one region that has been of interest for a long time is understanding what the role of spiral arms as sort of this galactic scale process and how that impacts molecular gas formation and star formation. And so again, taking some recent results from the FANG sample, this work by Jia Soon shows that there is an enhancement in the molecular gas surface density, again mapped in CO2 to 1, in the spiral arms traced by the blue as a function of galactocentric radius. There is an enhancement relative to the interarm regions. But this is still a little bit unclear from within our own Milky Way, including some very recent results by Dario Colombo. And of course, one of the big challenges within our own galaxy is understanding what the spiral structure actually is and the sightline complexity and distance ambiguity. So what we'd really like is to use the local group as our template to start to bridge between what we typically see in the Milky Way and what we usually see in the nearby galaxy population. So I'm going to split my talk into two parts at this point and talk about two now ongoing projects at different stages. The first, looking at whether with new VLA observations, whether we are reaching the sensitivity needed to not just trace the H1 in the disk near the midplane, but start to trace and resolve on higher spatial resolutions the surrounding neutral ISM environment about the disk. And the second part, I'll show some very preliminary results of a project that we've been building up to over the last several years. And that's using our top-down view in M33 to explore what the anatomy of a spiral arm is, again, at high spatial resolution. So I'll start here with the larger scale, looking at the 21 centimeter. So the map that I'm showing here is the product of observations taken in the last decade by the VLA. And so in particular, it really takes advantage of the VLA's upgraded correlator. And so the biggest difference, as you might imagine, this is an iconic galaxy that has been studied in the H1 various times with many telescopes, including the VLA. The biggest advantage with the upgrade was our ability to get a much larger bandwidth for the H1 while still achieving a very high spectral resolution. And so in this map that I'm showing here, the individual channels are only about 200 meters per second. So in previous M33 observations, we're reaching more like 1.2 or 2 kilometer per second channels. The reason why this matters potentially for the atomic ISM is that we expect there to be cold and warm phases of the atomic gas, and a 200 meter per second channel corresponds to resolving thermal line widths below 100 Kelvin. So in theory, you have the ability to resolve between cold and warm gas, at least as much as you can in emission. So we're coupling a very high spectral resolution with sort of equivalent or better surface brightness sensitivity with previous observations. And so this is both the VLA plus GBT short spacing. This is from Jay's much larger map that I'll show in a few slides. So I think to appreciate this a little bit, I like to look at this in sort of 3D. And so this is a 3D rendering of the emission. It's downsampled a little bit, and that's why it looks a little blobby. But what I've done here is I basically tipped it, and we're now looking at velocity roughly along the y-axis. And so most of what probably catches your eye is the large galactic structure of M33, mostly seeing the rotation curve and velocity. But you can start to see that there are other features that we're starting to pick out in this map. And in particular, when we convert that to what we see in sort of individual spectra, we're seeing a lot of different spectral features that are suggesting that we're not just tracing the bright H1 near the midplane of the galaxy, we're seeing other features connecting to the larger environment. This larger environment has been studied in great detail for a number of surveys. So again, taking an image from Jay's paper from 2012, showing the much larger GBT map, looking for H1 or an H1 bridge between M33 and M31. And there have also been a number of surveys, I'm going to highlight a couple with Sibo, looking more immediately sort of just around M33. So roughly this map that we're looking at on the right is, I probably should have put up a square instead of a circle, but it's roughly this region around M33. I think it's a little bit larger actually. In any case, what we're looking at on the right is the structure of high velocity clouds, either associated with M33 or potentially the Milky Way, with respect to M33's velocity. So M33 is just hidden here in sort of this outer contour showing the extent of the disk and the warp disk. And the colors that you see here are the velocities, either blue shifted or red shifted, of these features that have been detected with respect to M33. So a significant number are blue shifted, particularly Wright's cloud off to this side. But in total, you can see that there's just a significant amount of H1 structure that you can trace at very high surface brightness sensitivities. So we can zoom in a little bit more, in this case, looking at, again, a narrow Sibo survey from earlier work by Grossi. I've picked this out mostly to highlight that while a lot of these clouds are sort of seen off away or more distant from M33's star-forming disk, there are a number that start to appear that are along a common sightline with the bright star-forming disk. So mostly M33 has been sort of I think minimized just to show this extra structure, but to give you an idea of what we see in the disk itself in this more extended component, we see this bright middle region here, and then there's this outer portion here. And this is definitely part of M33. It can be well modeled by a warped disk component. So it's this broader extended structure that is certainly connected. Now, what we see in the VLA observations, in order to reach a fairly high sensitivity, we're really just only looking at where you see the sort of saturated component here. So we're going to be limited on what exactly we can link to on these larger scales, but we can look at common lines of sight to see if we're starting to find hints connecting the bright structure to the surrounding environment. And so just to highlight this, this is the, again, the integrated intensity or the column density map here on the left. And to give you an idea of the typical spectra that we see, I've just grabbed 4 at various points within the disk. In this case, this is corrected for short spacing with the GBT. So what I want to highlight here is just qualitatively that the shapes are not sort of limited to sort of a single Gaussian that you'd expect from a thermal and turbulent broadened component. We see a lot of different features starting to arise. So these top hat-like shapes, or flattened like shapes, multiple components potentially. And the part that I'm really going to focus on and the importance of the short spacing information is a lot of these lower surface brightness features, these extended line wingtails, and what we can learn from those. So the usual way that you'd look at this, so in our case, we're combining the data through feathering, as you normally do. And so if we look at this in terms of the column density, it's perhaps not too surprising. You see more structure, particularly on the outer edges, once you combine the short spacing information. And similarly, if we look at individual velocity channels and calculate what the total flux is, shown here on the Y, against the velocity, we can get an idea of how much flux was missing. So it's somewhere between 50 to 70%, depending on the channel. So I realized I didn't put a sort of GBT only comparison here, but we are able to basically completely recover the entire flux that was present in the GBT map, at least within the limits of where we have VLA data. And so from here, I'm going to actually split into 2 parts for this project to talk about the importance of the short spacing information. So I'm going to come back to this environment and these high velocity clouds and focus first on where does the short spacing information, what does it add to these individual spectral shapes or shapes that we find in individual spectra. So I've grabbed, again, 2 examples here on the left. The dark line is the combined VLA plus GBT, and the gray line shown underneath is what we see from the VLA only. And I've downsampled it a little bit just for this comparison. So what you can start to see is that the bright structure is fairly similar. It's not too different, but where we start to see more differences is these extended tails that's arising from much larger scales. So this one's particularly prominent. And so this is changing the structure of these individual spectra. And it's most prominent in these extended line wings. And what we found is that this is part of a much larger sort of galactic scale structure, but we have the sensitivity to find this in again, individual H1 spectra. So these are the 2 spectra that I showed before. And what I'm demonstrating here is that these tails they're asymmetric, and their shape or the direction that they're asymmetric depends on the position in the galaxy. So this spectrum taken more in the northern half of the galaxy tends to have this redshifted excess. This is towards the systemic velocity. And in the blue half, we tend to see a larger blue shifted component. Again, this is directed towards the systemic velocity. So the map that I'm showing on the right, this is a measure of that asymmetry, and it's color coded again by the red and the blue shifted sides. And so this is opposite of what we find for M33's rotation curve. The northern half of M33 is its blue shifted limb, and the southern half is its red shifted limb. So what we're finding is an excess in these tails that's pointed towards the systemic velocity. And so what this likely is that we're starting to trace the fainter H1 that is more, is found at a higher disk scale height away from the midplane. And as it gets farther away from the midplane, it starts to rotationally lag. The short spacing information is really, really crucial to sort of make this connection. And so I can show what this skewness parameter looks like before and after the short spacing correction. So on the left is the VLA only. You can see that it has some structure similar to the red and the blue halves that we see with the combined data. But largely it ends up being due to smaller scale structure, not sort of larger halves of the galaxy. So our ability to recover this larger scale structure in the H1 farther off the midplane really critically relies on adding the short spacing information. But because it also affects it obviously affects the shapes of individual spectra, it also starts to affect the most common kinematic estimates that we typically use in extragalactic H1. And so this is coming from the usual moment analysis, where your moment one is a weighted mean. It's the velocity weighted mean by the brightness temperatures. That was interesting to get through. Or it's just your centroid velocity. The second moment, or its square root, is typically what we measure for something like the line width. So if you're dealing with sort of a sparsely sampled H1 spectra that is roughly in a Gaussian shape, these properties should correspond to something similar to what you see with the temperature or the velocity at peak temperature, and roughly the Gaussian line width, or the width of an equivalent Gaussian. However, these things start to break down as we get these more and more complex spectra, and it's interesting to see how some of our most commonly used methods start to break down in the presence of this complexity. And so the lines in particular are very important here. And so if I start with the centroid, if we have these asymmetric lines that are due to this larger galactic scale pattern, this rotating or this lagging rotational disk, what we find is that the additional tails will move the centroid velocity from close to the velocity at peak temperature, the center, the brightest component. And I've exaggerated this example a little bit. You can see that the extended line wing will tend to pull it just to one side, biased by the asymmetric component. The difference actually ends up being quite dramatic. And so I'm showing here in this plot, this is the difference between the centroid velocities calculated with and without the short spacing from the GBT data. The color bar is actually quite large. It's going from plus or minus 20 kilometers per second. And you can see that it roughly has the same structure that we're getting from the skewness parameter, that the northern half is a more redshifted component, so it's biased towards the redshifted part, and vice versa in the southern half. So this looks quite different. It does actually end up having just a mild effect on what you'd estimate for the rotation velocity, but it's certainly something to consider for these very nearby galaxies like M33. So I'm showing results of tilted ring fits to M33's rotation curve using different inputs. So either using the centroid velocity from only the VLA data or the VLA plus GBT. Those are the solid lines. And the dashed line is using a different metric for the center of a line. It's simply the velocity at peak temperature. I've just called it peak velocity here. And you can see that three of them are largely on top of each other. The one that stands out is the centroid involving both the VLA plus the GBT data. Those asymmetric line wings tend to underestimate the velocity, and this shows up here. This is pretty mild. It's a difference of about 2 sigma or so. But when modeling the mass components, for example, and with increasingly great data, we do have to start being concerned about limitations like this. So ideally, you'd maybe want to move from, instead of this sort of simplified disk fit, to a more three-dimensional model, trying to include this information from the lagging component and maybe some parameterization for how the rotation velocity changes with disk scale height. The other key parameter that we typically measure is the line width from the second moment. And if you add these increased line wings, it does just tend to broaden what you'd interpret as the line width of the H1. So the blue solid part here, this is on the y-axis, the H1 line width versus galactic centric radius. So each point here is a azimuthal average along sort of disks within, or sorry, rings within the disk. And you can see that the solid line traced by just the VLA is quite a bit smaller in line width than the combined VLA plus GBT. So just to guide your eye, we typically talk about extragalactic H1 line widths roughly on kiloparsec scales of somewhere between 10 to 12 kilometers per second. And if your warm neutral medium is about 6,000 Kelvin, it has a thermal line width of about 6 kilometers per second. So this excess is typically interpreted as the kinetic turbulent energy. And so we use that to compare to different injection sources for this turbulent energy. So this difference, which is about 50% between these two curves, would end up implying that your estimates of the turbulent energy change by about a factor of 2. This is a fair bit, but there's a lot of play in our understanding of the injection mechanisms for turbulence. So typically we look at and compare it to the energy that we expect coming out of supernovae explosions. But there's an additional fudge factor or an efficiency factor that we don't have fantastic constraints on. And so this sort of factor of 2 play is still within the uncertainty that we expect from energy from supernova injection. So what all of this really argues is that, and it's maybe a little bit obvious from looking at those spectra and the more complex shapes that they have, it's really just saying that there are properties and enough information in the data that we really need to go beyond very simplified estimates of the kinematics to use something that more incorporates the full spectral shape that we can interpret and understand what is the larger galactic structure and the atomic ISM physics that we're actually tracing. So we're starting to see this sort of rotationally lagging disk likely from H1 farther away from the midplane. And so that begs the question that I raised earlier of, do we start to see some of these more significantly offset high velocity clouds or other neutral ISM structures in the vicinity of M33? And we can start to see that there do appear to be hints of this. So to demonstrate this, I've taken a position velocity slice. This is just a small slice along M33's major axis. And these green triangles are to guide the eye. This is M33's rotation curve here. And so in the contours, we can see that one side tends to be more elongated than the other. This is that rotationally lagging component, this excess line wings. So we see it on both sides. But we also start to see in the lowest contour, maybe the hints of some of these high velocity clouds that have been before really only traced by these very high surface brightness sensitivity single dish surveys. So we see some of it here, and we're getting close to the noise level, but there's perhaps some structures over here as well. So to overcome being right at our signal to noise threshold, what we can do is basically just average over a much larger range of velocity. And at that point, we do start to recover some of these high velocity cloud structures just within the sight lines towards where we have the VLA observations. So only the center of M33 really. I put a question mark here because we haven't looked in fantastic depth about what they could be or the relationship, but there is some suggestions here that they are related to M33 because these coherent-like structures that you're looking at, the velocities here is an offset from M33's rotation velocities. So the rotation curve has been corrected, and then we've sort of averaged over, I think, about 90 kilometers per second just to boost the signal to noise. So in the north, we start to see a few structures, and these roughly match what we see in some of those single dish surveys, but now we're starting to resolve some of the structure closer to 100 parsec scales. In the south, there's this curious looking feature, and while it's largely offset, the sort of the different parts of emission that you see here do pretty much span 90 kilometers per second. So there's a wide velocity range. If it were to be sort of some sort of coherent physical structure, it looks sort of like filamentary and would have a length of 6 to 8 kiloparsecs. So take that with a large grain of salt, but it's perhaps an interesting structure that we're just having difficult tracing at our sensitivity. As we get closer to the center, though, this structure does get closer and closer to M33's rotation velocity. So I'll just show one more example. There's one very bright potential high velocity cloud that stands out far more I think than the rest. And in the Arecibo map, in the larger warp disk, we see this sort of northern warp or northern arc component. And where it seems to be sort of increasing in the column density towards the sort of bright disk, we do find this high velocity cloud-like structure here. And the reason that this is potentially interesting is if we look at an average spectra taken within this red circle, it's one of the only features that really clearly is sort of intersecting velocity with the main disk. So this cloud component is this green fitted Gaussian, and the red dash or dot dash is the component from the disk. So this is centered again on the rotation velocity here. So this is potentially something quite interesting to look at. We're a little bit limited here in trying to provide the link to the larger warp disk, primarily because it gets faint and we're reaching the edge of where we actually mapped the VLA. So just to end off in this structure or in this section, I wanted to highlight that there's still a ton of things that we can start to look for in this data. This is really sort of just looking at what we see on the surface. So if I take this 3D rendering and I instead change the contrast so you can really start to see a lot more of the faint structure, you can see that there is just a ton of structure here. In particular, if you can look closely, hopefully the video is running well enough over Zoom, but there are sort of these wispy features, and they're quite small. They appear to be quite localized. And so it'd be interesting to follow up with more detailed kinematic modeling to see if these are related to, for example, recent star formation, perhaps tracing an atomic outflow on localized scales. If I turn the contrast down a little bit, you start to see some of the more prominent sort of offset structures or potential high velocity clouds. This big clump here is the one that we are looking for, the one that's potentially intersecting the disk. And so all of this is just putting this all together is that the GBT observations are really crucial to pick up this fainter structure. It's not clearly identified in the VLA observations alone, but combined with the increased sensitivity and spectral resolution from the new VLA observations, we are actually starting to trace into this regime where we can detect not just the bright H1 associated with the disk, but a little bit more to the immediate environment around it. And so I wanted to just briefly advertise that there's more to come in this direction over the next several years. And so we've started this extra large VLA program, the Local Group L-band survey, or LGLBS, as a large team. And we started observing just this past, I think we're on our second semester of observations with the VLA. So to reach these sensitivities, we essentially just need a huge amount of VLA time. And this was really only possible with one of these quite large programs. So over the next 3 years, we'll be using about 1,800 observations in all 4 VLA configurations. And we'll be targeting all 6 of the northern star-forming local group galaxies. So this is out to about a megaparsec. So I've showed M33 sort of in the middle here, but we'll also be tracing essentially the entirety of M31. As you can imagine, it's the largest target. It takes up by far the most amount of time. And we'll be adding to this the 4 star-forming dwarfs that the VLA can see. So this is IC10, WLM, NGC 6822, and IC 1613, which are particularly interesting because they span a different range in star formation rate and are much lower metallicity systems. So over the past semester, we've been focusing a little bit more on the dwarfs to begin with, a much smaller field of view. So these are some of the very early looks at some of our H1 observations. These are moment 0 or column density maps of all 4. And we're looking at roughly 100 parsec scales here. And some of the sort of wispy-like features that we were looking at before in M33, they're starting to become apparent in all these dwarf galaxies too. So we're quite hopeful that there's more to come in this direction with the observations that we've already taken in this larger project. So just to end off, I've talked a lot about the H1 components. So part of this will be reaching slightly higher resolutions, about 20 parsecs instead of the 100 parsecs that I showed here. And the VLA's fantastic flexibility in the correlator also allows you to get the full 1 to 2 gigahertz radio continuum with polarization. So this will really be taking advantage of the long baselines with the VLA to reach roughly arc-second scales. So that offers much improved supernova remnant catalogs from the radio. And ideally, this would mean detecting H2 regions or having the sensitivity to detect H2 regions coming from individual B stars. So this is the end of this first part. I wanted to stop and see just if anyone had any questions before I move on.
So we did have one quick question in the chat, which is, would you be observing at the GBT as well? So yeah, it appears that, so we've gathered together the existing GBT H1 observations from all these targets. So far as we can tell, those already reached the sensitivity that would be needed for combining with the VLA. Basically, the time needed for the GBT observations, even if we needed a little bit more, is pretty small. This would be well within just a regular proposal if more is needed. All right, Ilseng, feel free to unmute yourself.
Yeah, just a quick question. So, Eric, is your observation consistent with the other observation, especially for the edge-on galaxies?
That is a great question. It's not something that I have explored, so I don't think I can answer that right now. I think in thinking about this and how you would, instead of just model the disk, but model an actual 3-dimensional structure, I think we probably can start to provide some constraints and then compare that with the with edge-on galaxies. I'm a little bit unsure of how well you could constrain. I was thinking about this a little bit yesterday, and I'm wondering how well we can constrain disk scale height from these extended line wings versus needing to sort of ascribe an actual structure to this disk scale height. I think there might be some degeneracy there, but I do think that there are ways with the current data to make that comparison.
Yeah, thanks.
All right, and then I actually had a quick question for you, Eric.
Sure.
So for these wispy cloud structures, what sort of timescales do you expect them to be at?
So these were the what was coming up in the video. Is that right?
Yeah. It's like, how old do you estimate them to be?
I'm not too sure. And part of this is, so I've done a little bit more complex spectral modeling. And one of the issues in sort of separating out these extended line structures with something like a Gaussian decomposition is that in some places it sort of is this single extremely broad structure just to account for the extended line wings. In other cases, it's split up into multiple components. It does seem to be almost everywhere. And so what I suspect is it's a mixture of probably multiple things. In some cases, it is probably an outflow near regions with a lot of massive star formation. So there's a couple of giant H2 regions, especially. But in other cases, it could also be sort of an unresolved high velocity cloud population. So I think, I'm not quite sure on sort of putting an exact time scale, because I think it's probably 2 or 3 things mixed together.
Mm-hmm. Okay. Thanks.
All right, so I'll continue on to the second part, which is much shorter, I should point out. So this is some preliminary results of sort of now starting to zoom into just one portion of M33, and that's looking at the anatomy of a spiral arm. The idea and the importance of a spiral arm has been noted for a long time, including theoretical work stretching back to the 1960s. In particular, there's one paper that I particularly like to look at by Roberts in 1969. And what this is showing is just taking a couple of figures from the paper. This is a model for the Milky Way showing the spiral arm structure with a certain pattern speed. And the idea that as you go into the potential minimum of the spiral arm, you get a shock in the gas, increasing its densities. And so you expect downstream from the arm to have star formation resulting from the increased density. This figure on the right is sort of the unwrapped version of what's going on in the picture on the left. So the x-axis would be the azimuthal variation. And you can see in the bottom is the spiral arm potential. And when you reach the bottom of that potential, you expect the gas to shock, increase the density, and then have newly born stars, H2 regions downstream from the arm. Now, when I say spiral arm structure, M33 is maybe not the first galaxy that comes to mind. It's a very well known to have a flocculent spiral structure. So just as a demonstration of this is a Galaxy far ultraviolet map. And you can see there's these sort of spiral arm fragments, they've been called, in the outer disk. But when we reach to the inner disk, there does appear to be maybe some more coherent spiral structure. Excuse me. And there are also various examples of this. I just grabbed one from an early H1 interferometric observation by Rogstad from the 1976. And they have written, this is H1 on sort of 2 arc-minute scales, which actually matches quite well the large structures that we see. It's very nice data. And what they've done is they've added these 2 log spirals tracing 2 arms. And you can see that they go through certainly some of the structure, but it's a little bit, it's not as prominent as you'd expect from a grand design. So why M33? Well, again, its proximity in our local group means that we can zoom into small regions to basically start to trace down sub 10 parsec scales. And we have some hints that the inner spiral structure is somewhat more persistent. This is some recent results from the HST Fatter survey. And what we showed is that if we separate, sort of make a rough separation in the age of the stellar population, so these maps are showing the densities. You can see that in the old and intermediate populations traced by RGB and AGB stars, you do start to see, again, it's not very prominent, but you start to see this sort of spiral structure going on. And the younger population, it's probably a lot harder to see. It's a lot clumpier, more sparsely sampled, I think, in a lot of cases. But this gives us a hint that while the spiral arm structure may be weaker than what we'd expect elsewhere, there is some sort of persistent spiral structure that we can use to answer the question of and test longstanding theories. So the way that we went about this, sort of building up data over the last several years, we decided to zoom in on this one box here. And this pink line in both the images is a fit to the IRAC 3.6 micron data tracing the old stellar population. So it's fit to that with a log spiral to give us some indication of where the spiral arm shock could be located. The background here is from one of the HST bands. You can see some nebular emission from young massive stars and much finer structure, likely from the dust extinction. But we didn't have great constraints on the H2 kinematics here traced by 12CO2:1. So this is from the larger scale map from the IRM 30-meter telescope. We're basically resolving about 50 parsec scales. So this is still roughly just in large clumps. So what we did is we used NOEMA to go from 12 arc seconds and now start to resolve 2 arc seconds in 12CO2:1. So 2 arc seconds here is about 8 parsec scales. And you can see that these blobs are suddenly resolved into individual clouds or structure within clouds. That gives us a much better sense of what the spiral gas near this, what the gas near the spiral arm is actually doing. And so some early work, we did what you usually do with CO structure, and we created a cloud catalog from the emission that we see here. And so we can look at the properties of some of these clouds from downstream of the arm, this is the northern part here, to the upstream component to see if the properties do change with respect to where we think the spiral shock is located. And what we find is not necessarily a clear result. So I'm showing in these panels on the left, the x-axis is distance mapped out from the spiral arm. Each individual point is one cloud found in the structure. And then these thicker black lines are a binned median. So in terms of cloud mass, we don't really see much of a difference, suggesting that the arm is not clearly building up more molecular gas on these scales. We do, however, see a hint if we look at the line width normalized by the radius of the cloud, so it's proportional to the turbulent energy, that there is maybe some hint that it increases near the arm. Now, of course, these are fairly small number statistics. You can see there are a few outliers here, but still suggestive of that general picture of the turbulence increasing. There's a shock at the spiral arm, and that increases the turbulence in the gas. So what we expect from modern star formation theories is that the increased turbulence will broaden the probability distribution function of gas density, and we should see an increase in the dense gas fraction then if we're going from one side of the arm to the other. And so this is where our Argus project comes in. So in 2019, we started mapping the same region that we earlier observed with NOEMA in 13CO1:0, and especially critical here, HCO plus and HCN 1:0 at about 90 gigahertz. So from our initial observations, we got a detection towards the brightest 12CO source. And in the coming weeks, later on in the semester, we're hoping to finish mapping this area so that we have reached the depth that we're hoping to get to and have several individual line of sight detections. So this orange line here is sort of 3 sigma towards an individual spectra, and the darker orange line is where we detect over 5 sigma detections. And so the most interesting thing about this is if there is a relationship with the spiral arm, this dense gas gives us a really interesting and more direct connection with star formation that is potentially triggered by the arm. And so the broad idea is that with these Argus observations and adding new JWST observations in the coming, hopefully about a year, we now have the data set to go from over a large range in ISM density to both the embedded and exposed star formation on sort of molecular cloud scales. So I showed the H1 data before. And so the idea is if there is a relationship with where we see the spiral arm, and if it is sort of increasing the gas density leading to star formation, we can use this as a sort of clock to see when each of these stages occurs by by relating that to the distance from the spiral shock. So we're quite hopeful, and I'm very excited for this project. And with these new Argus observations plus JWST, it sort of completes the set to explore how this spiral arm in M33 is affecting star formation and the dense ISM. And so with that, I will just leave you with my conclusions. So I showed two parts of looking at M33 observations at 1.4 gigahertz, the importance of the short spacing from the GBT when we look at H1 and nearby galaxies. As we get increasing sensitivity, the spectral lines become more complex, and our basic kinematic measurements start to, the assumptions underlying them start to break down, and we need more detailed modeling. And what we're starting to see is that on 100 parsec scales, we're starting to detect sort of the broader environment around M33. And the second part, I just showed very preliminary results that we're now getting with this top-down resolved view of M33's southern spiral arm. And our upcoming Argus and observations are sort of providing that missing link, getting closer to the beginning of the star forming phase so that we can test how star formation in the neutral ISM is affected by that spiral shock. So I'd be happy at this point to take additional questions, and thank you all for joining.
All right. Thank you very much, Eric, for both components of that fantastic talk. So once again, open it up to the audience. If you have a question, just feel free to unmute yourself. Looks like we've got two hands raised already. Let's start with Jay.
Yeah, very nice talk, Eric. I was curious at the high velocity clouds that you're identifying in M33 actually have relatively low velocities. The 50 kilometers a second or so on relative to the disk. Do you see much higher velocities?
I've done a quick check, but I wouldn't say in great detail. It wasn't obvious that we were detecting anything at much higher velocities, for example. So I tried to connect with the AGES results, the Keenan 2016 paper, and some of the structures that they were seeing, I think, are just at far lower column densities that we can trace here. So I think with this LGLBS, we're going to be re-imaging the data and adding to it. And I think that's probably the best place to explore if we're seeing higher velocity clouds.
Okay, thanks.
All right, and Ilsang, you have your hand up as well.
Yeah, so the spiral shock can accumulate a mass and might enhance the star formation, but other people might say that those increased turbulent energy actually prevent the mass collapsing to form the stars. And what do you think your observation will constrain? Do you think will constrain in either of those hypotheses, or you just think that observation strongly prefer the one or the other?
I think so. I think there's two parts in putting together the multi-wavelength data set in tracing the different ISM phases to star formation downstream. I think the first part is checking to make sure that there is sort of some clear relation suggesting the spiral arm is playing some role through it. For whether or not that increased turbulence actually leads to star formation, we should be able to look at that by mapping how the dense gas fraction varies using those Argus observations. So I think we can do that in two ways. For the HCO plus that we just expect to be bright enough to detect towards individual clouds, we largely expect that's going to be coming from within the clouds that we've identified at higher resolution in the 12 CO. So we can try to link what we see in the Argus observations, the one coarser scales, to the individual clouds to see if the dense gas fraction changes within individual clouds across the arm. The other way is that because we have again, the 12 CO, and with respect the distance to the spiral arm, we can probably go about doing a stacking experiment to increase our sensitivity. And so I think that will give us more of an average result of whether or not the dense gas fraction is varying. And if that does actually lead to some apparent triggering of star formation or not.
Yeah, thank you.
All right, and Eric, I just wanted to bring your attention. There's a comment by Pedro Salas in the chat where he just says that the position velocity rendering that you showed, particularly the WISPs, look a lot like outflow simulations from Evan Schneider's talk last week at the NRAO Colloquium.
I haven't directly looked at that, but yeah, I think there's a lot of work to do here and try to make those connections. There are difficulties in, I think, modeling and trying to figure out which part would actually be coming from an outflow versus which part is actually coming from some other process or this rotationally lagging disk. I think we can do it. And then once we can start to separate out where these components are potentially coming from, yeah, that would be absolutely wonderful to then directly compare with what you're seeing in simulations to see if they're similar or not. I think it's going to be especially interesting for some of the dwarf galaxies that we're looking at and sort of in that lower metallicity environment. If we see, is there increased outflows in sort of following expectations at low metallicity?
Well, it sounds like you have your work cut out for you.
Luckily, there's a big team working on this.
That always helps. All right, so one last check. Jay, I don't know if you still have your hand up or you have another question. But if there are any other questions from the audience. If not, then it is at the hour right now. So thank you once again, Eric, for joining us today. Greatly appreciate hearing you talk. And for those that are interested, next week we will have Stella Ocker giving a talk on her latest research. Thank you very much, everyone.